What is the specific problem that the proposed method, Hopfield Boosting, aims to solve?
The specific problem that the proposed method, Hopfield Boosting, aims to solve is out-of-distribution, OOD, detection in machine learning systems. Hopfield Boosting leverages the energy component of modern Hopfield networks to advance the state-of-the-art in OOD detection. The method addresses the issue of encountering inputs that deviate from the training distribution, which can lead to erroneous predictions if not properly classified. By using an auxiliary outlier dataset, AUX, to boost the model's OOD detection capacity, Hopfield Boosting aims to improve the performance at the OOD detection task by learning a boundary around the in-distribution ID data. The goal is to classify examples that are not part of the training distribution as OOD, enabling the system to notify users when no prediction is possible or trigger a manual investigation. Hopfield Boosting achieves this by sampling weak learners using modern Hopfield energy and incorporating informative outliers close to the decision boundary during the training process.
How does the proposed method, Hopfield Boosting, work, and can you illustrate it step by step?
Hopfield Boosting is an out-of-distribution OOD detection method that leverages the energy component of modern Hopfield networks, MHNs, to improve OOD detection. The method uses an auxiliary outlier dataset, AUX, to boost the model's OOD detection capacity by learning a boundary around the in-distribution ID data. The process involves sampling weak learners using the modern Hopfield energy, MHE, and updating weights to draw mini-batches from the AUX dataset for training. The method computes an energy function, E_B, to determine the strength of a specific learner, with higher energy indicating a weaker learner. The training process involves training a classifier on the ID data using cross-entropy loss and adding an OOD loss using the AUX data to sharpen the decision boundary between ID and OOD regions. The model parameters are updated based on the composite loss, and the sample weights are updated iteratively. At inference, the OOD score is computed using both ID and AUX data, and the model's discriminative power is evaluated using metrics like FPR95 and AUROC. Hopfield Boosting outperforms other OOD detection methods, especially when sampling weak learners close to the decision boundary, demonstrating its effectiveness in improving OOD detection performance.
What are the theoretical or practical benefits of using Hopfield Boosting for OOD detection?
The theoretical benefits of using Hopfield Boosting for OOD detection lie in its ability to leverage the energy component of modern Hopfield networks, MHNs, to efficiently detect out-of-distribution OOD samples. Hopfield Boosting utilizes the energy function to estimate the dissimilarity between a query pattern and the stored patterns in the memory, allowing for the identification of OOD samples based on their energy levels. This approach enables Hopfield Boosting to learn a decision boundary between in-distribution, ID, and OOD regions, improving the model's OOD detection capability. Additionally, Hopfield Boosting incorporates an auxiliary outlier dataset, AUX, during training to enhance the model's ability to detect OOD samples, further refining the decision boundary. Practically, Hopfield Boosting outperforms state-of-the-art OOD detection methods, such as POEM, by significantly reducing the false positive rate at 95% true positives, FPR95, on datasets like CIFAR-10 and CIFAR-100. The boosting step in Hopfield Boosting, which samples weak learners close to the decision boundary, contributes significantly to its superior performance, showcasing the practical benefits of this approach in improving OOD detection accuracy. Overall, Hopfield Boosting's innovative use of MHNs, coupled with boosting and auxiliary outlier data, makes it a powerful and effective method for OOD detection, offering both theoretical soundness and practical performance improvements in real-world applications.
How is the method validated or tested in the paper?
The method proposed in the paper is validated through extensive experiments on various datasets, including CIFAR-10, CIFAR-100, ImageNet 1K, and several OOD datasets like SVHN, textures, ISUN, places 365, and LSUN. The validation process involves training the model using the ID dataset and an auxiliary outlier dataset, then testing the model's OOD detection performance on unseen data distributions. The OOD detection performance is evaluated using metrics like the false positive rate at 95% true positives, FPR95, and the area under the receiver operating characteristic, AUROC. The model is validated by comparing its performance to other OOD detection methods, such as POEM, EBO-OE, MIXO, DAL, DEVO, DO, and DOSE. The experiments show that the proposed method, Hopfield Boosting, outperforms these baseline methods, demonstrating its effectiveness in detecting out-of-distribution samples. Additionally, the paper discusses the influence of boosting on the performance of Hopfield Boosting, showing that informative outlier sampling significantly contributes to the model's OOD detection capability. The validation process also includes ablation studies and analysis of challenging datasets to assess the robustness and limitations of the proposed method.
What results were achieved with Hopfield Boosting in terms of FPR95 on CIFAR-10 and CIFAR-100?
Hopfield Boosting achieved significant improvements in terms of FPR95 on CIFAR-10 and CIFAR-100. Specifically, on CIFAR-10, Hopfield Boosting reduced the average false positive rate at 95% true positives, FPR95, from 2.28 to 0.92. On CIFAR-100, the FPR95 was decreased from 11.38 to 7.94. These results indicate that Hopfield Boosting outperformed the previous state-of-the-art method, POEM, in OOD detection on both CIFAR-10 and CIFAR-100 datasets.
What are the limitations or drawbacks of the Hopfield Boosting method proposed in the paper?
The limitations or drawbacks of the Hopfield Boosting method proposed in the paper include the need for tuning hyperparameters, such as the value of beta and lambda, for each ID data set separately, which can be time-consuming and require manual intervention. Another limitation is the computational overhead during inference when computing the OOD score S, ASHI, especially when using the full ID dataset and a randomly sampled subset of the AUX dataset. Additionally, the method relies on the assumption that the ID and AUX datasets are representative of the training and out-of-distribution data, respectively, which may not always hold true in real-world scenarios. Furthermore, the method requires a large amount of memory to store patterns from the ID and AUX datasets, which may be a limitation in resource-constrained environments. Lastly, the method's performance may heavily depend on the choice of the encoder and neural network architecture used, which could impact its generalizability across different tasks and datasets.